right, so we are completely switching gears today. If you found the last couple of classes kind of confusing, well, you know, the last couple of classes felt a little bit different in that I was more showing you things that are true without explaining them too carefully, just so I could show you some interesting combinatorics. Starting today, we're gonna kind of come back to the ground a little bit and do some things that are a little bit more standard and yeah. So let's just start with that. Actually, can you guys do me a favor and open those blinds so that we get a little bit more light? So for the next few lectures, we're going to be talking about posets. And actually, the other thing that happened is that you might have noticed in the last couple of classes that I wasn't following the books. I was actually just kind of following texts that I know are out there. And I'm going to post on the blog some links for some reference material on that. But today we're actually coming back to the book. So we're coming back to Enumerative Combinatorics, Volume 1. And this is Chapter 3 from posets. Okay? So what's a poset? Poset is short for partially ordered set. So this is something that I only realized after a few years of thinking about posets. I realized that it's called poset because of this P, this O, this set.
I saw
Did you all know that?
Time, yeah. Partially ordered set.
Oh, but I taught you guys what a poset was. So I mean, I knew, so I told you. But when I learned about posets, nobody told me that that's why they were called posets. I mean, I think most people know. I think I was just kind of ditzy in figuring this out very late in life. Anyway, so it's worth mentioning in Spanish, this is conjunto parcialmente ordenado. And so actually, in some of the Spanish literature, they're called copos. I don't like that name, and I think most people don't use it. Actually, in Spanish, often people just say poset. But if for some reason you're reading Spanish literature and you find a copo, then maybe that's what it means. Actually, I think it's only in Mexico that they do this. But anyway, so posets, partially ordered sets. So the idea is that this is a set P with a binary relation less than or equal such that first, x is always less than or equal to x. Okay. Second, if x is less than or equal to y, and y is less than or equal to x, then x is less than or x and y are the same element. And finally, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z, or x, y, z. Okay. So these properties all have names. This is the reflexive property. This is the antisymmetric property. Antisymmetric because in relations that are symmetric, you have this if and only if this. And here it's the opposite of that. You never have x less than y, y less than x. And then this is called transitivity. So and basically a lot of the class today is going to be spent just introducing a lot of terminology. Okay? So let's just maybe I'll just go quickly through this stuff, and if you have any questions about any of what I'm going to say, let me know. But so we're going to say that x is less than y if x is less than or equal to y and is not y. We're going to say x like this, okay? And this is red. Y covers x. If x is less than y and there is no z such that it's between x and y. Okay? And so, and now the Hasse diagram of the poset is obtained by drawing an edge from x to y whenever x is covered by y. Okay, so you join cover relations, and you always put the small element below and the big element on top. Okay, and so we're gonna keep some examples here. So the first example is written by a bold n, where n is some integer. So these are the numbers from 1 up to n, where this is the usual order. Okay. So for example, if I want to draw 4, then my cover relations are 2 covers 1, 3 covers 2, and 4 covers 3. Okay? And so this actually is called a totally ordered set because any pair is comparable. Okay? The second example is the subsets of the numbers from 1 up to n. Okay? And we say that the order is containment. Okay? And so for example, if I want to draw B3, then I need to draw the subsets of 3 elements by containment, and I get this picture. So I get the empty set, the single elements, the pairs, and the whole set. Okay? And it's worth remarking that if you do this for a particular value of n, then what you're going to get here is the skeleton of the n-dimensional cube. Okay, so if you want to draw a 5-dimensional cube, then you should draw this poset for n equals 5, and that's going to be it. Okay. So that's another important example, and this is maybe a better example to keep in mind because it's not totally ordered, and that's kind of the key about this is that the keyword here is partially, and that in a partially ordered set when you have 2 elements. Really, the point is that the 2 elements might be that this one is less than this one, or maybe that this one is less than this one, or it might be that they're incomparable. And that's the difference with usual orders. Okay? So for example here, 1 and 2, 3 are incomparable. You cannot decide which one is bigger than the other according to the order of containment. Okay? Third example is the divisors of n. Okay? And our order is going to be divisibility. Okay? So, for example, we could do the divisors of 84. Okay? And they're going to be ordered by divisibility. So, what are the... Maybe we'll start from the bottom, okay? So how do you draw this? Well, there is a unique smallest element in this poset, which is 1, right? 1 divides everybody, and so in this poset, 1 is less than everybody. What goes right above 1? The smallest things according to divisibility are the primes, right? But only the primes that divide 84. So which ones are those? Well, we should work out what 84 is. So 84 is 2 times 42. 42 is 2 times 21. 21 is 3 times 7. Right? And so the primes that divide 84 are 2, 3, and 7. Okay? Okay, who else divides 84? In the next level, I'm going to get the products of 2 primes. Okay, so I get 2 times 3, which is 6. I get 2 times 7, which is 14. And I get 3 times 7, which is 21. Any others? The other one is 2 times 2, right? So where should I put 4 here? Well, 4 is a multiple of 2, and it's not related to anybody else. Well, I guess it's a multiple of 1. But 4 covers 2, and then there's no relation with the other ones. So I put it there. Okay, now I get the products of 3 primes. Okay, so it might be 2 times 3 times 7, which is 42. Right? So 42 is a multiple of these 3, but it's not a multiple of 4. And then who else should I put here? Well, for example, 2 times 2 times 3, right? Which is 12. So where does 12 go? Let's say we put it over here. And who is it bigger than? It's bigger than 4. It's a multiple of 4. And it's a multiple of 6. Right? But it's not a multiple of the other ones. So that was 2 times 2 times 3. And then I also need 2 times 2 times 7, which is 28. And that is a multiple of 4. It's a multiple of 14. And it's not a multiple of the other ones. And those are all the products of 3 primes. And then finally, I get the product of all 4 things, which goes up here. So I get, okay. So that's the poset of divisors of 84. And you see that it takes this nice shape of a, kind of like a box, right? So while we keep talking, you should think about why that's the case. You can imagine that this is not an accident. This is a general phenomenon. Okay. Another example that's very important is the partitions of the set of 1 up to n. Okay? And here I mean set partitions. So how can I order two set partitions? How can I say that one is bigger than another? If you think about it for a little while, I think you will arrive at the idea that the most natural rule is refinement. What that means is that you have your set from 1 up to n, and you partition it into pieces. Okay, so now you have your pieces, and now you take those pieces and you partition that further. Then that should be a finer partition. Okay, so that's going to be the order. And so let's do it for given that I only have this much space, we're going to do it for n equals 3. Okay? So we have our whole set. Okay? Now let's say that we split it we split it as little as possible. Okay, so we're going to split it into 2 parts. Then there's 3 things that I could do, right? Just leave the 1 alone, or leave the 2 alone, or leave the 3 alone. Now notice these are not order partitions, right? So 1-2-3 is the same thing as 2-3-1. That's why there's only 2 possibilities. Okay? And now what I'm going to do is that I'm going to allow myself to partition these things further. Okay? But you see that no matter which one I choose, if I partition it further, then I'm going to get the complete partition into single pieces. And so this is the partition poset pi 3. Okay? So I said the order is refinement, right? But if you notice, actually, going up is not refinement, it's the opposite thing. So we're going to call it coarsening. Okay? So when you go up the poset, what you're doing is that you're merging parts. Coarsening. So merging parts. As you merge parts of your partition, you move up your poset. Okay? So do you guys have any questions about any of these 4 families of posets? Mm-hmm.
For number 4, in this example, when you went down from the top to the second level, you split as little as possible. But if we have like a bigger partition, or sorry, at each level, we're accounting for all possible splits, such that each way we're splitting into that many parts. So like if we take 1, 2, 3, 4, 5, if we want to jump down one level, we could actually split it into 3 parts.
That's right. So I mean, the thing that's a little bit boring about this example, and I'm repeating Tahir's question as I answer it. The thing that's a little bit boring about this poset is that if you have a set of 3 elements and you want to partition it, then you either partition it into 1 piece, 2 pieces, or 3 pieces. And so here they are: 1 piece, 2 pieces, 3 pieces. And now for a bigger value of n, then like if n is equal to 5, then I'm gonna get like first just the single partition 1, 2, 3, 4, 5, the trivial partition. Then in the next level, I'm gonna get all the partitions into 2 parts. And now they're not gonna be so simple. I mean, it's all the ways of splitting the set from 1 up to 5 into 2 parts. And you might remember this is actually the Stirling number 5, 2, right? And so on. And so actually, it is a good exercise. Not maybe. You should do, for example, pi 4 so that you know what it looks like, because this is a little bit too simple to see what this looks like.
At each level, we're going to split it out as little as possible. So that was my question. Are we even going to consider like?
I see. So maybe your question is this cover. Let's talk about the cover relation. Actually, I'll tell you my plan for the class is just to keep these pictures up here, and as I introduce lots of definitions, let's kind of check them over here. But I forgot to do it right now. So what are the cover relations? Well, here covering relation is just from k to k plus 1. Here, a cover relation is adding a single element to your set. Here, it's multiplying by a single prime. And here, the cover relation, I guess, is taking 2 blocks of your partition and merging them into one. Those are the cover relations. Okay. Cool. So more definitions. Intervals. The interval from x to y is what it sounds like. So it's the elements of the poset which are between x and y. Right, and that's the closed interval, and if you want you can define open intervals or half-open intervals, but usually in combinatorics this is the one that appears the most. If there is a minimum element, we call it 0 hat. Okay. And if there's a maximum, well, maybe. So let's talk about something that I know you've seen it before, but it's worth discussing it here. What is the difference between minimum and minimal? That difference is very important here. And the problem is that none of these examples illustrate it. So let's talk about this poset, for example. So a minimum element is an element that is less than everybody. So you see here, there's no minimum. Right? Whereas all of these guys have clear minimums. You can still, the plural of minimum is minima, but that's going to get confusing since I'm trying to distinguish minimum and minimal. So anyway, here the minimum is 1, here the minimum is the empty set, here is the number 1, and here is the trivial partition into singletons. But here there's no minimum. Okay? What is a minimal element? A minimal element is one that doesn't have another one below it. Okay? And so these guys are minimal, they're just not minimum. So that distinction becomes more important in partially ordered sets than it was before. Okay. And of course, if there is a maximum, then we call it 1 hat. Okay. Now, a poset is locally finite if all intervals are finite. So what's this about? Well, actually, generally, almost all the posets that we're going to consider in this class are finite. This is combinatorics, and most sets that we consider are finite. But sometimes even combinatorialists consider infinite sets. Actually, there's a very natural infinite set that we consider all the time, which is the integers. Right? But somehow you want to say that the integers are still kind of discrete, right? Even, whereas the reals are less discrete. Yeah, I think it makes sense to say that combinatorics is more about the integers than about the reals. And this kind of makes this precise, right? So what is locally finite? All intervals are finite. So for example, if you look at the poset of integers, that's the integer line. Okay. Now imagine it going up now. And if you look at any interval, well, in an interval you're specifying a bottom and a top element, and the number of elements between is finite. Even though the poset itself is infinite, even though z is infinite, it's locally finite. So an example is the integers with the usual order. Okay? But a non-example is the reals with the usual order because you know that intervals on the reals are infinite. Okay? And so we tend to like locally finite posets better than the other ones to do combinatorics. And of course, all the examples that I drew there are finite, so we don't need to worry about that in our examples. Yep.
Can you give an example of a Hasse diagram that has no minimum element? Like
Every poset has minimal. Every finite poset has minimal elements.
no minimum element.
No minimum. This one.
Okay,
But I guess in terms of what would that represent? I guess not an example based on that side, but like what would be an example that generates that poset? Order partition.
I see. So you want basically. I mean, this is an example of a poset with no minimum, but you're asking for a natural example that lives in combinatorics.
Context.
Order partition?
So ordered partitions, for example. There's a natural order on ordered partitions, and that order doesn't have a minimum element. Lots of things actually. We'll see examples like that. Okay. It's very usual to define, for any mathematical structure, to define substructures. Okay. So subposet. What is a subposet? Well, actually, there's two possible definitions of subposet, and one is stronger than the other. So there's two versions. Induced subposet is what? So it's going to be a subset of P, okay, where with the order induced from P, right? So if you want to know whether X and Y are comparable in your subposet Q, then actually you just look at whether they're comparable in your poset P. Okay? So maybe it's worth doing a quick example here. So maybe P is this, and maybe Q consists of these 5 things. Okay? But the point is that if you're an induced subposet, then you choose your elements and the order is forced on you. Okay? So the order is just whatever it was over here. Right? And then we have a weaker version weak subposet, which maybe I'll call it R, and maybe we'll do an example with the same subset. Okay. And the point is that now you have the extra flexibility that you don't have to have the same order here as you did here, but it should be a subset of the order here. Okay, so you can only be less than or equal here if you were less than or equal over there. So, for example, I might have this and this and this. So the point is that if x is less than or equal to y in my weak subposet, then it's not, okay, this is not an if and only if, but it is an if. If I have a comparability in R, then that must have been a comparability in P. Okay, so these are the differences between induced or weak subposet. Okay, and generally speaking, we don't really care too much about this property. This is too weak of a property. It's not that interesting. And this is the property that we usually want to consider, being an induced subposet. Okay. Let's talk about isomorphisms again. Another very usual thing to define for any mathematical structure. So P and Q posets are isomorphic if there exists a bijection phi from P to Q which respects the order such that S is less than or equal to T in P if and only if phi of S is less than or equal to phi of T. Okay. Now, as usual, definitions of isomorphism look more complicated than they are. It's isomorphic if it's the same thing. Right? That's always what isomorphism means. And then you have to write something like this, but really, it's just that when you look at it, it's the same thing. So, for example, what's an example of an isomorphism? The divisors of 42. What is that isomorphic to? 3q. Divisors of 42. Actually, well, this illustrates both definitions, right? So this is the divisors of 42 are an induced subposet of the divisors of 84, right? Because you just look at this part of the poset, and the order relations are the same. And when you look at it, you see that it looks just like this one. And so therefore, the divisors of 42 are isomorphic to B3. Okay. By the way, I didn't say it, but this is sometimes called the Boolean poset. Or the Boolean lattice.
Specifically for 3 or just for?
No, for n. So this poset Bn is called the Boolean poset.
Is that why it's a B?
That's why it's B, yeah. Okay, more definitions.
Is it just curious, is it true that D of n be isomorphic to B of k if its prime factorization is 3?
That's right. So the reason this is true is that this is the product of 3 different primes. 42 is the product of 3 different primes. And it won't be too hard to convince yourself that if you have a number that is the product of k different primes, then its poset of divisors is isomorphic to the Boolean poset pk. And actually, in a second, I'll talk about what this is also, when the primes are not necessarily distinct. So what's a chain? A chain is something isomorphic to this. Let me give you this definition. So it's a set such that x1 less than x2. This in almost everything that we're going to do is for finite posets, and that's why I define a chain to be finite. But if your poset was infinite, then you could have infinite chains. Okay, and so I could make another definition, which is to say that a chain is a set where every two elements are comparable. Okay, and that sounds a little bit more abstract, but it's in the finite case it coincides with this definition, and in the infinite case it's just it's just a totally ordered set. But we're only going to care about finite chains, so that's why I just write it like this. So a chain is just you go up in the posets from 1 to 2 to 42 to 84. Let's say. Get the chain. Okay, and the opposite thing is an anti-chain. Such that xi and xj are incomparable. For I different from j. Okay. So what's an anti-chain here? Something like 4 and 21, or even 4 and 42, or 4, 6, 14, and 21. Any set that has no comparisons between it. Okay.
So in this case, it's like all these.
And so one example in all of these cases is if you take all the things that height k, those are all incomparable. We're going to talk about heights in just a second. Actually, that's the next thing we're going to talk about. So how do we define, because I guess the next thing I want to say is this, that you look at these things and they have heights, right? But how do we make that precise? They have floors, right? This is floor 0, floor 1, floor 2, etc. And the way of making that precise is to talk about the rank of the poset. So the rank of the poset is the size of the longest chain. Okay. And then we're going to say that a poset is ranked. Let me just say, the way that you should think about this is it has floors. It has well-defined floors. Okay, this is how you should think about this. But now I'm going to write some definition that is equivalent if any interval all the maximal chains have the same size. So how do we reconcile these two things? I think the best thing to do that is to show an example of something that is not ranked, and then we'll see what goes wrong. Okay? So Often the best way of understanding what something is just to see what it is not. Okay. So what is a non-example? A non-example is something like this. This poset. Okay. What is the rank of this poset? It's 3. The longest chain takes 1, 2, and 3 steps. Okay? But the problem is that you can also take this shortcut that only takes 2 steps. Okay? And so, why is this not ranked? Because I can find an interval, namely from here to here, such that there are 2 maximal chains of different length. This maximal chain has length 3, and this maximal chain has length 2. They have different lengths. Okay? And so ranked is something where, maybe what we should do next is say, okay, if I satisfy this property, then how do I define the floors? Well, what I could do is I could say, let me look at the minimal elements, and they all are on floor 0. Okay? Minimal elements. I don't know, there might be 3 minimal elements. Okay? And then, I can say, given an element x, what is its rank? So, if I poset is ranked, actually, I think I'm doing something slightly wrong here. Let's see if I.
I have a question.
Yep.
If you didn't define floors and you want to think about preserving this rank idea, can you imagine like going from one point and just picking some other point and all the paths that you can take to it? Like there has to, like those sets of paths have to have the same like distance almost?
Yeah, I think so. Let me show you what I was about to do doesn't work. The thing is that you might have a poset like this one. And this is a poset where the minimal elements are this one, and I don't want to have them both at rank 0. These kind of naturally want to be on different floors. Okay. And so what is the right way to do it? Well, I guess that what we can do is we can say, okay, just pick an element, okay, and say it has rank k. But we're gonna choose k later, okay? And then we say, if you have things that are less than that element, then the rank of this, so if y is less than x, then the rank of this guy is gonna be, well, you just see, okay, if this takes L steps, then I'm going to put this guy in rank k minus L. Right? And the point is that from y to x, there is a unique number, which is the length of the longest paths. Okay. And so then I can define the relative rank between any 2 elements that are comparable one to the other. Okay. And then what I can do is that I can look at my Hasse diagram, okay, and I can consider it as a graph. And I can say, I think it's essentially what Krista was suggesting, which is that you can kind of say, okay, well, then I can just keep traveling around my poset and just say, okay, well, let's take something else that's smaller and just figure out the rank of this guy. Okay. And then maybe now I look at something bigger than this guy, and okay, so if from here to here it takes me 3 steps, then this is going to be rank this one minus 3. And I keep doing this, and I can basically define the relative rank of anybody that's connected in the graph If I consider the Hasse diagram as a graph, then anything in the connected component of x I can reach by going up and down chains, up and down maximal chains. And so by doing this, I'm going to have determined the level of each element. Okay? So again, maybe it's worth doing an example of what I'm talking about here, right? If I want to figure out what the ranks of this poset are, then I say, and okay, I can make it a little bit more interesting. I can say, okay, let's get this guy rank k. And then that means that when I go down this chain, this has to be k minus 1, k minus 2, k minus 3. Because this is the maximal length from here to here. Okay? And similarly for any maximal chain from here to here. Okay? Now if this is k minus 3, then when I go up the poset, this has to be k minus 2, k minus 1. And if this is k minus 1, then this has to be k plus 1, k plus 2, k plus 2, k plus 3, right? And then I just have to decide what value of k to give it, and so I choose k so that this guy is at level 0. So I say that k is equal to 3. Okay? And if my poset happens to have several connected components, then I just do that for each connected component. So I get my levels. So that's how these two things are equivalent to each other. All right, so that's ranked. That's what a ranked poset is. Or sometimes we call these graded also. So maybe we should go over here and say, what are the ranks? Okay. Well, these guys all look ranked to us, and actually, it's very easy to say what the ranks are. Okay. Here, the rank of a number is the number minus 1. Right. This is rank 0, rank 1, rank 2, rank 3. Here, the rank of a set is the size of the set. 0, 1, 2, 3. Here, the rank of a set is the number of prime divisors with repetitions, if there are repetitions. And here, the rank is, I guess, n minus the number of parts in the partition. All right. So let's define some operations. If P and Q are posets, then P plus Q is just a poset on the union. Okay, so I'm thinking that P and Q are posets on disjoint sets, and then P plus Q is just going to be basically, I think this is clearest in an example. This poset plus this poset is just this poset. You just put P here, Q here, and they're not related to each other.
Do you try to match the ranked? Do you try to match the
So if P and Q are ranked, then P plus Q is also ranked. Okay, in the natural way. And P times Q is the poset on the set P times Q, where S, T, or maybe so they sound like elements of P and Q. So if I take a pair PQ, and I want to know if it's less than or equal to some other pair, okay? And this is a comparison in the product poset. Well, this is true if and only if P is less than or equal to P prime in my poset P, and Q is less than or equal to Q prime in my poset Q. Okay? So we already talked about, what did we multiply? We multiplied something in this class. We took the product of, is it graphs?
Combinatorial classes stuff.
Yeah. So this is going to be, I'm trying to remember, at some point we were talking about how the cube was a product of the edge with itself n times. I forget what context we were talking about. That. But in any case, the product here is kind of, I'm going to do it and it's going to seem very familiar, right? So let's multiply this guy times maybe this guy. Okay? So what I do is that I put a copy of my red poset on each vertex of the black poset. Okay, so in other words, I put this and then this and then this, right? One for each copy over here, and then I join, because there's an edge from here to here, there's a black edge from here to here, then I draw a black edge from here to here, here to here, from here to here. And similarly, I get black edges from here to here, here to here. So that's the product. And again, it's easy to see that if P and Q are ranked, then the product is also ranked. Yeah.
So this would be different if we switch the order of the interval?
It's a good question, and it's actually not different. So it might seem like this procedure. It might seem like I favored the red by drawing it first, but if you do. If you draw it with the black first, you get the same thing. It's just that I drew red small and black big, so they look different. But that's so you could see what's going on. But this construction is symmetric in P and Q. And actually, you can see it from this definition, right? From the definition, it's clear that they're the same. But my claim is that this is how you draw the Hassett diagram, and that's a symmetric procedure. Okay. So let's see what else can we define? Well, maybe let's talk about what dn looks like. Okay, so what does dn look like? Let's say that this is the prime factorization of n. Then what is dn isomorphic to? Well, so Servando was telling us what happens if the alphas are all equal to 1. But in this case, we have an alpha that is not equal to 1. Right? The prime 2 appears twice, and that means that we got kind of a change in this direction from 1 to 2 to 4. And in general, what's going to happen is that, I mean, you can think of this as being the product of the chain from 1 to 2 to 4, the chain from 1 to 3, and the chain from 1 to 7. This is the 84 is isomorphic to the chain from 1 to 2 to 4 times the chain from 1 to 3 times the chain from 1 to 7. Okay. And why is that actually? Well, it's because if you take a divisor of 84, then it must be, what's the prime factorization of a divisor of 84? It's one of these elements times one of these elements times one of these elements. And these elements are ordered like this, and divisibility divisibility of integers just depends on the primes. A divides B if each prime appears more times in B than in A. And so that means that we get this statement. Okay, so this was supposed to be bold. Alpha 1 plus 1 times alpha 2 plus 1. These are the chains. And, well, you know, okay, so I mumbled something about why this is reasonable. But yeah, you should just, to make sure that you're understanding the technicality of how this works, you should actually write a proof to make sure that you know how to do that. Now, one other thing that I want to discuss is the rank. So if P is ranked, the rank generating function is, I forget what letter Stan uses for this, but let's use R for rank. It's the sum over the elements of the poset as to the rank of the poset. Okay, so you're just counting how many things you have in each rank, as the name indicates, right?
The coefficient?
Yeah, so another way of saying it is that the coefficient of x to the k is the number of elements of rank k. So I can write this as sum of ak x to the k, where this is the number of elements of rank k. Right? So what is the rank generating function of a chain? Well, this is just 1 plus x squared up to x to the n minus 1. Actually, let's use q, because as you can see, if we use q, then this is going to be the q analog of n. And this n is this boldface n, right? What about the rank generating function for the Boolean poset? Well, here this is just the sum over k of the elements of rank k are the subsets of size k. So you just get 1 plus q to the n. What about this one? Well, let me show you one explanation of this 1 plus q to the n. This Boolean poset is the product of n chains. Right? The chain from empty to 1, the chain from empty to 2, the chain from empty to 3. In the same way that I argued about the divisors. The rank generating function of this interval is 1 plus q. It's 1 plus q. For this one is 1 plus q, for this one is 1 plus q. And that explains why I get 1 plus q, 1 plus q, 1 plus q. And therefore, this is going to immediately tell me that this is hold on, did I do this right? If I have a prime appearing, yeah, I did do this right? If a prime appears twice, then I get the chain of size 3. So if a prime appears alpha 1 times, then I get the chain of size alpha 1 plus 1. So I claim that rank generating functions are multiplicative. And so if I want the rank generating function of these, then I just need to multiply these, which I already know. So I just get alpha 1 plus 1 Q analog, alpha 2 plus 1 Q analog, alpha n plus 1, alpha k plus 1. Okay. Okay. And use a proposition that I'm using, which is that if P and Q are graded, ranked, then the rank generating function of P times the rank generating function of Q is the rank generating function of the product. Okay, that's a nice exercise that you can check. Okay, and then finally, the rank generating function for the partition lattice. Okay, well, sum over k of q to the k times the number of partitions of rank k. Okay. So how many partitions of rank k are there? What's the Stirling number? Right. If I want rank k, then I want to have n minus k parts. Because this is 3 parts rank 0, 2 parts rank 1, 1 part rank 2. So if I want rank k, I need to have n minus k parts. So, okay. So those are my rank generating functions. All right. And so if you have any posets that you ever run into and they're graded, it's always a nice thing to try to check and see if this rank generating function gives you something nice. And you can see that, at least for these simple examples, they're all very nice and simple. Okay. A poset is called a lattice if any elements x and y have a least upper bound which is denoted like this, and a greatest lower bound, which is denoted like this. So for any x and y, you need to have these two operations of join and meet. So this one is called join of x and y, and this one is called meet of x and y. So that means that you have these two special elements for any x and y. Join and meet. And so what does it mean to be a least upper bound? Well, it means first of all that you are an upper bound. Right? So this guy needs to be bigger than x and y. But the other thing that it means is that if you have any other upper bound, z, and if z is bigger than x and is bigger than y, then Z has to be bigger than the least upper bound. Okay, and similarly on the other side. So another way of saying it is that the upper bounds of x and y have a minimum element, and that minimum element is this guy.
Oh, yeah.
Just a joint.
Do they have to be comparable, all the upper bounds?
No, so there might be other bounds that are other upper bounds that are not comparable among them, but there is this one special one that is less than all the others.
Less in, as in like lower rank, or
Less in the poset.
okay. But if they're not comparable, then what does it mean to be less than?
If they're not comparable, then this is not satisfied.
So x join y is going to be a supremum.
So x join y is, I mean, I don't want to use the word supremum and infimum, but they're similar. But there might be small technicalities that I'm not thinking very clearly right now. Because I haven't thought clearly about the differences between this and a supremum or an infimum. There might be slight differences, but yeah, so let me say it again real quick. So least upper bound is an element called x join y, such that it is bigger than x, it is bigger than y, and if you consider any other bound, any other upper bound, z, that is bigger than x and is bigger than y, then that other upper bound has to be bigger than or equal to this one, which is the least one.
And here when you say bigger, you don't mean by rank, you mean like inequality.
I mean whenever I said bigger,
order.
I mean bigger in the partial order. This is extremely important to keep that in mind whenever for the rest of the class, that when I say bigger, I don't mean that a set of size 2 is smaller than a set of size 4. I mean bigger in the poset. Right? So I guess I'm doing it informally, but when I write less than or equal, I say that it's bigger or smaller.
Question.
Yeah.
Do you know why? Like, I feel like the least upper bound should have. Right? 'Cause that's the
This is the yeah. Why is this like this and this like this? You might say, well, this guy is kind of shaped like the other way. That's what you're saying, right?
Yeah.
That this thing is a V, yet when you draw it, it's upside down. The reason is that it's supposed to emulate union and intersection. Right? And so that's the way to remember which one is V and which one is what is. I'm forgetting right now how you write this in LaTeX also. So this is V and this is wedge or
There's cup and
cup. Anyway,
Got
I'm sorry.
cap.
Okay.
big cup and big cap.
Okay, so the point is that you make this definition, but now this gives your poset an algebraic structure because now you have these operations, right, which you can think of as algebraic operations. Right? They're binary operations that take the input is 2 elements and the output is 1 element. So maybe it's worth doing examples again. So in 1, what is... And okay, the other thing is that it's... Anybody who ever learns this, I think for a while we always forget which one is join and which one is meet. And that, anyway, this is join, this is meet. You can come up with your own reminder. But anyway, so examples. In poset 1, what is is it a lattice? Do I have, for any 2p and q, do I have a least upper bound? Like the least upper bound of 2 and 4, or let's say of 2 and 3. The least upper bound of 2 and 3 is 3. It's the bigger one. And the meet is the minimum. So this is a lattice. Okay. For subsets, this is union, and this is intersection. And you see these take the usual form that if a set Z contains a set X and it contains a set Y, then it contains their union. And dual. Okay, what about 3? It's 3 elements. Do any 2 elements have a join? Is there a... Actually, what would it be? It would be a smallest common multiple, right? There's a name for that. It's least common multiple. Least common multiple. And the other one is the greatest common divisor. And again, it's not entirely trivial that these are true, but in a number theory class you learn that if Z is a multiple of X and Z is a multiple of Y, then Z is a multiple of the LCM. And dually with the GCD. Four, is this a lattice? So if you have 2 ways of partitioning a set, is there, what is it? Finest coarsening of them? And dually, is there coarsest refinement? This, play with it, you'll see that actually, yes, it makes sense, but the only way to really see this is to just do some examples. So what did I say? To go up, I need something that is coarser than both, but I need it to be as fine as possible. So this is the finest coarsening. And the meat is the coarsest refinement. Okay. And so I would suggest that you take, I don't know, the set, take 2 partitions of 9. I usually stop at 9 because once you throw in 10, then you get confused about whether it's a 10 or a 1 and a 0. So take 2 partitions of 9 and make them not trivial, make them kind of interesting partitions. And think about what is the finest coarsening and what is the coarsest refinement. And I think you'll see what they are, and I think you'll convince yourself that they do satisfy this property. But this is really one of these things that the proof just says, I don't know, sit down and think about it for a couple of minutes. I think that's clearer than anything that I would try to write. Or I should say, actually, I mean, there is a kind of a general abstract nonsense proof where you just write down a proof and it makes sense as a proof, but to actually reconcile that with what the example is not so clear. And I think the clearest thing is just to do an example and you'll see how this goes. Okay. Well, it looks like we're out of time, so we're going to stop there, and next time we'll talk a little bit more about